You build the fastest trains on Earth and you set them on a pile of broken rocks. Not because nobody thought of anything better, because nothing better exists. That's the part that should stop you for a second. We live in an era of carbon fiber, reinforced concrete and precision-engineered steel. Yet every major railway network on the planet, from the freight corridors crossing the American heartland to the commuter lines threading through Tokyo, sits on the same loose bed of sharp grey stone it always has. Look down at any set of tracks, anywhere in the world, and there they are. Jagged, unglamorous, completely unreplaceable. And here's the detail that makes this even stranger. Those rocks weren't invented for trains. They were borrowed from an industry that had nothing to do with land at all. But before we get there, because that part earns its place, you first need to understand why nothing else works. So let's start with the problem you don't see until it's too late. Why do tracks sink? A fully loaded freight train doesn't just press down on the ground, it negotiates with it. You're talking about a rolling mass that can push past 1 million pounds, locomotives, then car after car of steel coils, grain, shipping containers, all of it moving as one continuous force. Place that weight directly onto bare soil, and the ground doesn't hold. It yields. Pressure concentrates at specific points beneath the ties. The earth beneath compresses unevenly, and one small dip becomes a larger dip. A slight misalignment becomes a real one. And when rails drift out of true, trains don't send a complaint. They leave the track. That rock layer, engineers call it track ballast, exists to interrupt that chain before it starts. The rails rest on the ties rest on a thick bed of crushed stone. When a train passes, the ballast catches that concentrated force and fans it outward across a much wider footprint. Think about pressing a single knuckle into a firm mattress versus laying your open palm flat. Same pressure, completely different outcome. The ballast is the open palm. By the time that force reaches the actual ground below, it's been distributed enough that the earth can absorb it without moving. But weight distribution is only the first job. Here's what most people miss. How does ballast protect rails? Tracks aren't supposed to be rigid. A rail line bolted to an immovable concrete slab sounds safer until you think about what happens to it. Every wheel that rolls over the track sends a shockwave through the system. Multiply that by hundreds of trains, thousands of wheels, millions of passes. A perfectly rigid foundation doesn't absorb that energy. It stores it in the metal, in the fasteners, in the ties, until something cracks, loosens, or warps. Ballast gives the track a controlled amount of give. Each stone can shift microscopically under load and return. The track breathes instead of breaking. Steel adds another layer to this problem. In summer heat, rails expand. In winter cold, they contract. If they're locked into a fixed base with nowhere to move, that thermal stress builds into what railroaders call a sun kink. The track buckles sideways into a shape no train was designed to handle. The ballast bed holds the ties firmly enough to keep geometry correct, while still allowing the tiny movements that let steel respond to temperature without tearing itself apart. And then there's water. Put track on bare dirt, and heavy rain turns your foundation into a slow-moving disaster. The ground softens, shifts, and washes away in sections. Seal it under concrete and water pools instead of escaping, sitting against steel and timber until rot and rust do what floods couldn't. A bed of stone does neither. Every gap between those jagged chunks is a passage. Rain hits the surface and falls straight through, draining away from the ties, keeping the subbase dry and stable, regardless of what the weather decides to do. That same stone layer makes it nearly impossible for weeds to establish roots, and roots left unchecked will leave a rail out of alignment just as effectively as any flood. So now you know what ballast does. But here's what nobody tells you. The shape of those rocks is just as deliberate as the bed itself. And the reason comes down to a property of stone that engineers stumbled onto before they fully understood why it worked. That part is next. Now. Why are the stones jagged? About those rocks being jagged. You might assume that's just how crushed stone comes out. It's not. It's the specification. Smooth, rounded stones, the kind you'd pull from a riverbed, behave like loose ball bearings under vibration. Every passing train would slowly stir them, and the track would drift. Crushed granite and quartzite, broken into sharp, angular pieces, do the opposite. Their edges catch on each other. Corner locks against corner. The whole bed becomes a mass that resists lateral movement even when a high-speed train hits a curve and sideways forces try to push everything outward. Sharp is the engineering. Rough is the requirement. Size matters too. Ballast stones run roughly 1 to 2.5 inches across. Large enough to resist getting pulverized under constant load. Small enough to pack together and still leave drainage channels between them. Softer rock breaks down faster, fills those channels with fine dust, and eventually turns the whole bed into a compacted layer that neither drains nor flexes. Which is why when you see those massive machines creeping along a track, the ones that make your commute crawl, they're not doing construction, they're doing restoration. Lifting the track, shaking the stones through screens to remove the fines, packing everything back down level. It's called tamping, and without it, the system that makes ballast work gradually becomes the system that causes it to fail. Here's where the story takes a turn you didn't expect. Where did ballast come from? The word ballast didn't originate in a railroad engineer's office. It came off the water. Centuries ago, wooden ships leaving port without cargo faced a serious physics problem. A vessel riding too high in the water is dangerously unstable. It rolls, it catches wind poorly, it becomes unpredictable in swells. So sailors loaded heavy stone into the hull to lower the ship's center of gravity and keep it tracking straight. That weight was called ballast. When the ship reached its destination and took on actual cargo, the stones got thrown overboard or stacked on the dock. Over time, port towns accumulated enormous piles of this discarded shipstone. Cheap, heavy, already broken down to a useful size. When the first railroad engineers needed a material to stabilize their tracks, they looked at those harbor piles and recognized exactly what they had. Same physics, same job. The stone that kept ships steady on water was repurposed to keep trains steady on land. The name came with it. Why do we still use rocks? That lineage is still under every set of tracks you've ever crossed. The gravel bed in your backyard drainage channel works on the same principle. The crushed stone layer beneath the asphalt on the road you drove today uses the same logic. Weight distribution, drainage, stability. The sharp stones you felt through the soles of your shoes near a rail line are jagged for the same reason a ship once needed ballast. Physics doesn't change, and the solution that worked on the ocean still works on land 2 centuries later. Most of the world's railways still run on ballast, not out of tradition, but because when a section sinks or shifts, you add stone and tamp it back into place in hours. A cracked concrete slab shuts the line for weeks. Ballast is serviceable, adaptable, and everywhere. Some high-speed lines have moved to concrete slab track for the precision it offers at extreme speeds, and it works. But for the overwhelming majority of track on Earth, the answer is still the same broken rock that sailors threw off boats. You've walked past this system your whole life without knowing what it was. Now you do, and that pile of ugly grey stones is never going to look like nothing again. If there's something you walk past every day and wonder about, drop it in the comments. We read every single one, and the best suggestions make it into future videos. Don't forget to subscribe so you don't miss what's coming next.